And I said that solution mining is having that idea of trying to dissolve a mineral of interest to form a liquid. And that liquid is what will be transported for processing, where you don't need to go and do any crushing or at the end of the day do any other milling, because you've already gotten that liquid which you would have wanted to do milling to achieve. You are getting that already, so you skip crushing and milling when you use leaching approaches. So, and we said that with that one, we have two of them which we are discussing here. The first one is heap leaching. The heap leaching, I'll go ahead with drilling and blasting, haul the materials to a prepared platform, and then now subject that material to the solution or the liquid I think, or the chemical I think is capable of dissolving the mineral of interest from the heat. Then the water or the solution at the end of the day is transported to my processing plant for further processes. Then we have the second one, which is called in situ leaching. And I explained that the term in situ simply means in place. In place. So the mineral that I am interested in should be at where it is. I don't need to do any drilling and blasting to get it. It should be there. Then I'll find a way to just get a hole. That is the drill just a hole to get access to that deposit at that depth where it is. Now subject it to the chemical that can cause it to dissolve. Then after that, I fetch the liquid or the solution that is formed after the dissolution. I take that one for processing and get my mineral of interest. So let's break the system down now. So when we say leaching, leaching simply means trying to dissolve a mineral of interest to form a liquid. Trying to get a liquid form of a mineral of interest. So we have two types we are discussing here: in situ leaching and heap leaching. The in situ, the heap leaching is that I'll drill, and usually you do the leaching when you don't want to go through the process of what? Crushing and milling. Because when we drill and blast, we carry the material to the crushers, they are crushed and further milled at the plant. And then we add the necessary or the needed chemicals to dissolve the mineral of interest from some kind of a liquid form, and then we extract the mineral of interest from it. And this time around, we are using leaching. We don't want to do crushing, neither do we want to do milling. So we want to skip this process. And usually we use this in a gold mining if we think that a particular mineral we are interested in or the grade of a particular material is too low that we don't want to spend that energy, which is electricity and other things, trying to crush this, take it through our milling process and spend more, and at the end of the day get little. So then we go and dump this material elsewhere on a prepared platform using and other things as the background to avoid penetration of the dissolved liquid escaping onto the earth. We find a platform that will not allow that, an impervious platform. And then we subject it to the chemical we are talking of here that would allow this mineral to dissolve. And then the water that is obtained is processed. And that water is what we call the solution. So at the end of the day, we say solution mining. Good. Then we say the second one is what we call in situ. So to get the in situ, now we know what leaching is. And we are saying in situ. In situ simply means in place. So the mineral we want should be at where it is. So assuming the mineral is inside this container, I don't want to blast this container and get the mineral in it exposed to the atmosphere. Sometimes it may be for some reasons that the element I am interested in may have certain reactions with the environment, or its exposure to the environment or other external forces may be dire. And so I don't want that. So you allow the mineral to sit at where it is. Then you only drill a cautious hole to hit the deposit. Then you bring the chemical that it has been proven to be the master of this mineral that is capable of dissolving it, you subject it to it. Then at the end of the day, the liquid that is formed down there is sucked out to our processing plant for processing. And that is what we termed as in situ leaching. So I gave an example as salt. So let's assume you have salt inside this container, but then there's no means of getting to this salt. And you don't also want to break or destroy the container. So try to drill a hole in here at the top of this bottle. Pour some hot water inside there. And we all know that hot water can dissolve salt. So once it gets in there and it dissolves the salt and the salt turns into water, I can find a means to suction this water out and go and then heat that water. At the end of the day, after all the water content has evaporated, I get back my salt. And that is the idea of this leaching thing. So in situ leaching, let's look at this. It says that no solid waste is true because the materials is in place. We are not doing any drilling and blasting and hauling waste to waste dump, hauling or to whatever to place to go. No, we are not doing anything of that sort. So in situ leaching, no solid waste. Liquid waste, low concentration brine with no market value can be re-injected. So what they are saying here is that another advantage of this is that when, let's say, for example, it's a salt I am dealing with, and then I get the liquid or the water content and I realize that the salt in this water is too low, I can just heat this water back and eject it back onto the system to melt more salt. So re-injection is possible to do when you are dealing with in situ mining. Problems. Then it says little control of the solution underground and difficulty of ensuring the process solutions do not migrate away from the immediate area of leaching. That's exactly what Mr. Barney came up with. So if when you are doing this type of leaching, you don't have control of what is happening underground. And if you are not too sure that your chemical you are dumping in there, the consequence at the end of the day, you don't have an idea what extent of damage you are going to cause, then it is not worth doing this type of mining. Main impact of evaporate ILD derived from surface mining. So in situ leaching, ISL, is derived from surface or shallow underground contamination in the vicinity of evaporation ponds. Pregnant solutions can be highly corrosive. So what they are saying is that this type of technique is used for corrosive elements that you think that if you are to work with them face to face, maybe by the time you get the mineral, you yourself would have turned into a mineral. So it's very corrosive. And so you need to be, pregnant solutions can be highly corrosive and phytotoxic and can react with soil materials used in pond construction and may migrate to surrounding areas. So seepage may occur if the material is corrosive. It may eat into the soil and migrate into other areas you never expected it to go to. Then surface subsidence may occur. So the subsidence here is that when you do that and the whole body, assuming you are able to achieve your targets, the whole of that ore, just like I was demonstrating a deposit tilting to the left or to the right, and then this chemical gets in there, it will melt the whole block of material. You are able to suck it out. What will happen? The surface will begin to cave in. So you have subsidence. You don't see anything going on, but you see a particular area beginning to cave underground. And so it means something has gone on there. They have taken something out of that ground. So surface subsidence is also a disadvantage of this type of mineral. So we talked about heap leaching. Let me see if I can do. So this is the process of the heap leaching. They are using plastic lining to line the ground so that when they lay the materials on it, it does not penetrate to the ground. So heap leaching is a bit controlled. But when we come to the in-situ leaching, you can't control what is happening down there. And so this is some of the setup for heap leaching. So after you've laid all these processes, you have the platform, you dump the material, and this is what we call the heap. And then you begin to subject it to your chemicals. It leaches through these ponds, which will be collected later on for processing. So what are the advantages and disadvantages? Low capital and operating cost. So the low capital and operating cost here is that I will drill and blast, but I will escape crushing and escape milling. And so I will save some money there. Absence of milling step may require crushing and agglomeration. So sometimes when you blast, the particles may be too huge that the chemical may not be able to penetrate through the entire rock. And in that case, you have to go ahead with what? Your crushing, but you don't need to do milling. And in other cases, if you intend to undertake leaching, then it means that your drill patterns, when they are doing the drilling, you have to inform your blast engineers to make the bedding and the spacing, which we explained. The bedding and spacing should be close enough so that when you blast, you get smaller size materials that you could use for your purpose. Then can be used to treat low-grade ores. Yes, exactly what Goldfields used to do. So when the grade of that ore is too low, that you don't think that low material is worth going through your crushers and your milling process, then you bypass this thing. Then simplicity of atmospheric leach process. So you have a simple process for this, and absence of liquid solid separation step allows counter current operation, and metal tenor may be built up by recycling solution over heaps. Disadvantages, what are they? Let's talk about a few. So acid mine drainage. This is where maybe if there are some chemicals or elements already in the rock, and then when these chemicals come into contact with the atmosphere, they generate certain elements that can cause or provide or cause acid. And this type of acid in the mine, we say acid mine drainage. So I have elements within the rock. When they are exposed to the atmosphere, they transform themselves in a form to form some type of corrosive substance. And this type of corrosive substance, we say, is acid mine drainage. And they can be havoc. Then large footprint. Large footprint here is talking about where you have to set up several of these heap plants. So then we have large footprint. I was explaining the large footprint. The large footprint is where you have to create larger platforms, just like waste dumps, and be placing these materials here and there. And before you realize, a whole concession is filled with these things. And that's what we term as the large footprint. Then we have lengthy experimental programs. You cannot just get up and go and start it. You have to experiment, do a lot of lab tests to determine that, okay, if I do it this way, if I add this quantity, if I have a full truck of material, I need this quantity of cyanide or quantity of element that can help dissolve it. I need the particle size to be this or to be that. You realize that this particular one, the heap, it looks very soft. So I don't know whether after the chemicals they dumped on it that will dissolve and make it look as if it has been melted.